And as I'm taking a moment to look through the participant list, I think we might have the lowest turnout in all of the history of these No Fluff Just Stuff webinars, of which there have been many. We've been doing them every week for most of this year, and that doesn't surprise me. You know, one of the things I see that happens a lot is we tend to get fairly narrowly focused into, well, I'm working in this particular problem domain, and this is really what I want to focus on right now. So, what is relevant to that? And I wrote this talk because this is a topic that not a lot of people have heard about. And in fact, if you're in the room right now and you've never heard of this, I'm going to make the case that this is the most important technology in existence right now that you've never heard of. And over the next kind of 45, 50 minutes, we're going to go into why that is. And in fact, let's go ahead and dive right into the content. So this is what I would consider to be what I would call a big idea talk, and it's something that I'm really excited about. And in order to understand why this is such a big idea, I've got to give a little bit of context. I've got to give a little bit of background. So we're going to kind of break this into three parts. We're going to talk about kind of the history leading up to this moment that's going to frame why this is such a big deal and such an important topic. And then we're going to talk about some of the standards around this, and then what the implications of this ultimately are. So let's go ahead and jump in. And again, a quick introduction. My name is Michael Carducci, Carey. I spend my days as a hands-on software architect, and I get to spend a lot of time working on kind of cutting-edge stuff in a brand new sort of greenfield project. And to kind of give you an idea of what I do these days, I spend my time in the intersection between magic and technology. I don't know exactly what that makes me, but this is where I hang out. This is where I receive my mail. And to kind of frame this talk as we dive in, I'm going to start by saying this. I've been extraordinarily lucky 3 times over the course of my life. And I don't mean, found a $20 bill on the street. I mean, that's lucky, but these are things that were seemingly inconsequential, just happened to be at the right place, right time. And it's not even possible to start to see the implications of this until much later in life. These are seemingly random events that have shaped the course of my entire life. Excuse me. And the first one happened way back in 1986 at the Sweetwater County Library, and the Sweetwater County Library System, specifically the White Mountain Library. Growing up in the middle of nowhere in Wyoming, where I did, we didn't have access to a lot, and I grew up in a very modest household. Regardless, my folks wanted the best for myself and my sister, and whatever that meant, they tried to provide that. And one of the things that was really important, they wanted us to have books around the house. They wanted us to be a literate family, a family that reads together. That was just kind of a core value. And so, of course, we spent a lot of time at the library and took very deep advantage of what we had available in the middle of nowhere in Wyoming. But we would always participate in the library discard sale. And the discard sale would usually go on for about 2 weeks. And we only ever went on the last day. Again, modest means, modest household. We couldn't pay library discount retail, which is a laughably small amount. But we would go on the last day, because the last day they're just like, get these books out of here. Whatever it takes, just get them out of here. So the deal that they would offer is for $1, you could buy a fairly sizable bag. Imagine like a large size grocery bag, probably just slightly bigger than your average Amazon Prime Now bag. And you could put as many books as you could stuff into that bag you could have for that dollar. And as I traversed the various tables and things, one seemingly innocuous book caught my eye, and I tossed it into my bag on a whim. And that was Magic Digest by George B. Anderson. Just on a whim, I picked this book up. And that book, by the way, this is a fabulous, even today, a fabulous introductory course in Magic, teaching you a lot of fundamentals. And in fact, that book started a journey that I've been traveling my entire life. It's taken me around the world multiple times. It's put me on TV, film, radio. The effectively 5 cents that I paid for this book ultimately gave me a gross return on investment of well over $1 million in lifetime performance fees. This book also is directly responsible for my career as a developer, as bizarre as that sounds. And in fact, in a very real way, this book is why I'm here today. Just monitoring the chat here as well, just in case there's anything coming up in there. This book is why I'm here today. And it's been an amazing journey. I just, of all the random decisions that I could make in my life, this one has maybe had one of the most sweeping impacts. Number two was back in 1998. I was on a double-decker bus somewhere in Kensington, in London, in the UK, on the way to the magic shop, I should add. And I lost my balance and fell into this young lady's lap. And this picture was taken that day. And we started talking, and I forgot all about the magic shop. I spent the day with her instead, and just blown away. She was really something. Beautiful, charming, devastatingly intelligent, and we spent the entire day together. We wandered around the British Museum. It was a really wonderful time, and it was a day that I'll never forget, and it shaped so many things in my life. It's really just a shame that we lost touch all of those years ago. Although we did find each other again, and we got married in New Orleans last year. And again, just losing my balance on a double-decker bus in one random day in April in London changed the course of my entire life. But the third lucky thing was I had the insane fortune to grow up in this town, in this house, in this town, in this state. Now, you might be asking, well, what's so lucky about Wyoming? And to be fair, there are actually things to love about that state. But to outsiders, they might be hard to spot. And in fact, recently, comedian John Oliver went on a random tangent to just kind of dunk on Wyoming for a moment. And it looked something like this.
Were rejected in the primaries. That's practically an entire Wyoming disappearing into thin air. That is really bad. Unless, of course, it's the actual Wyoming disappearing, in which case it really might be for the best. It's a semi-arid sandbox filled with fluffy cows and nothing. The most famous part of Wyoming is the state trying to swallow itself up. And the second most famous part is it spitting itself out again. It's clear that even you don't like you, Wyoming, and it's getting hard for the rest of us to watch. And to be
You're muted.
Thank you for the chat. So, from the outside, that might seem grossly offensive to citizens of the great state of Wyoming. Now, I can't speak for everybody, but I can speak for myself, and I can speak for a lot of the people that I know. And on behalf of us, as a former Wyoming resident, I can say that we're mostly just grateful to have been noticed. But in that semi-arid sandbox full of fluffy cows and nothing, something was happening. And that something was the National School Network testbed. For those who are my age or older, you might remember that whole NSFNet thing that we used to call ARPANET that had started connecting universities and research institutions for about half a decade or so. Well, it was just about to have K through 12 schools connected to it as well. And there were a handful of schools across the country that were part of the pilot program. And in fact, Green River was the foundation of the National School Network testbed. It was the very first school district in the country to be connected to the internet. This is a quote. This is the vision that Jim Rogers, one of the local visionaries behind the initiative, had to say about the kind of ideas. Oh, what might this look like in a couple of years? I don't think anybody had any idea what the implications of that was actually going to be. But if you're anything like me, you might be thinking, wait, this town? an oasis of about 8,000 people in a high desert wasteland? This town that is largely just a lingering vestige of the Transcontinental Railroad? This town where the infinitely unflappable Phileas Fogg stopped briefly on his 80-day trip around the globe, and throughout the entire novel, Fogg maintained his legendary implacable calm, but just 5 minutes in Green River and he was ready to kill someone. Yes, this town. We were there for the dawn of the web. We were all present for the birth of the information age. And the visionary behind it, this guy Jim Rogers, just happened to live here. I cannot think of anything in my life more lucky than that. I mean, I think these three are a tie, but what insane luck. And as a result, I've had a front row seat to the revolution that is the web, and you have a front row seat to the next revolution. Now, maybe I'm overselling this. So let's actually look at that first revolution for a moment. You know, it started in 1969. We connected 4 computers together, a couple in California and one in Utah, I think. And over time, this grew and grew. By the early 80s, we standardized on TCP/IP, and by 1989, we were on the brink of having access to untold amounts of information. For example, if you were conducting an experiment at CERN in the late 80s in Switzerland, you could benefit from the results of simultaneous research and experiments happening on the other side of the globe instantaneously. The problem was, who is doing what research? Where is that research taking place? When was it added? How do you access it? The dominant application protocol back then was Telnet, meaning you'd have to connect into a custom app on a server, hosting its own custom information system with its own commands and quirks, with its own method of organizing information. Need to look somewhere else? Well, that was a PDP, and the next one is a VAX, so everything is going to be different. So somebody said, you know, we have a lot of these technologies out here. Why don't we just standardize on a couple of them? And so Sir Tim Berners-Lee wrote a modest proposal, a vague but interesting proposal, that maybe we should have a global hypertext system that we can standardize around. And he really very astutely highlighted the potential issues here. He said, the problem of information loss may be particularly acute at CERN, but in this case, CERN is a microcosm, a model in miniature of the rest of the world. In a few years, the rest of the world is going to have the same problems that CERN is having right now. And maybe in 10 years we'll have a solution, but we need something now. He very perceptively saw that there's so much valuable information just out of reach, and it was a problem that wasn't going to go away. And so this was proposed in 1989, and it kind of got ignored for a couple of years. And then by 1993, we started to get a little bit of momentum. There were 50 web servers. By 1995, there were already millions, and we had behemoths like Yahoo and eBay and even Amazon. And then today, we have self-driving cars, we have light bulbs that obey our commands, we have continuous revolutions in science and technology, we have access to the sum total of all human knowledge in our pockets. I'm looking for my phone, it's around here somewhere. But we have in our pockets, and we're connected to all of this constantly on a ubiquitous wireless 10 gigabit network. And I threw this slide up here more or less as a joke, but we actually literally have robots now that clean up behind us. In fact, I just got a text from Amazon. Today's promotion on the treasure truck is a Roomba. So how did we come so far so fast? The answer, very simply, is information made this possible. Think about it this way. As a developer, you're working on something and all of a sudden you're faced with an obnoxious, gnarly stack trace. What do? Do you start reading this? Do you maybe start spinning up a new app to wire up a little test harness to try to do some experiments and trial and error? No! We don't do any of that. Instead, we just ask the entire planet. And this is just a random Stack Overflow I pulled up for the purpose of illustration. But in this case, this was a developer in Pittsburgh, Pennsylvania, ran into an issue and asked the question. Less than an hour later, another developer in Paris answered. And then every single subsequent person who's run into this same issue didn't even have to wait an hour for the answer. They got it instantly. And it's incredible what we have access to and what we can collaborate on and the scale that we're able to collaborate it on. Now, I'm going to be honest, this is where I learned to program. When I ran into a problem, I lived in the middle of nowhere, Wyoming. I didn't have anybody to ask. Well, I could ask my neighbor, and I could look through a book or two that I happened to own, but that was it. There was no shortcut. You just had to keep banging your head against the keyboard until you finally got it right. And what's interesting is we romanticize this period. Like this is back when programmers were real programmers. And yes, there was a period when programmers were real programmers. We have some right here. There was a time when if there was a problem, there was literally nobody to ask, when every problem had to be solved the hard way. And that is undeniably impressive. I love this quote when Admiral Grace Hopper was being interviewed by David Letterman. He asked, "How did you know so much about computers back then?" And she very, very bluntly said, "I didn't. It was the first one." And today we get to stand on the shoulders of giants. We don't have, because of the people who came before us, these pioneers, we don't have to do this kind of heavy lifting just to make simple things work. And as a result, we do get occasional imposter syndrome. Like, am I actually a developer at all, or am I just really, really good at using search engines? But here's the thing. Does it matter if we're able to deliver the right results and deliver them quickly? Does it really matter? You know, because a quick answer, I don't see that as a bad thing. I don't see that as a failing. I see that as the next step in our evolution as developers. And you see this over and over and over and over again. Oh my God, you saved me weeks of struggle. You saved me days. You saved me days of headache. You saved me days. You saved me hours. You saved me months. And maybe these are slightly hyperbolic, but not really. I remember spending weeks on a problem that was the cause of a library that I was using that had a bug that wasn't documented. And the only way that I could get past it was to either write my own library or keep pounding against it until, oh, there's a bug here, I do this to work around it. Today, I'm just like, why isn't this working? It seems like it should. Stack Overflow, oh, there's a bug, do this, 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 and you can work around it. And it saves days and days of trial and error. So let's do some back of the napkin math here for a moment. Stack Overflow, as of this month, gets on average 262.1 million monthly visits. Now, obviously, they haven't always gotten that level of traffic, that it's increased over time. So let's be a little generous. Let's compensate on the next stack. So let's assume that of those visits, only 40% of the visits actually result in somebody finding an answer or getting the answer to a question. And let's also be cautious with our estimates and assume that every time you get an answer on Stack Overflow, it saves you about 4 hours of troubleshooting. If we add that up, that's going to be 12.5 billion questions answered and 50.3 billion hours saved. In real terms, because of the internet, we have saved 5.74 million developer years. That's 5.7 million years of developers doing this instead of developers doing this. It was information. And Sir Tim Berners-Lee so masterfully solved the problems that we had of information retrieval with his proposed mesh of information that we don't even think about it. The web works because we agreed on a simple set of standards. What kind of computer is it on? I don't know. I don't care. Where's that computer located? I don't know. I don't care. What operating system is it running? Probably Linux, but does it matter? No. What operating system am I using? Does that matter? Of course not. What browser? It doesn't matter. What software is serving the information? IAS, Apache, Glassfish, Tomcat, whatever. It doesn't matter. How is the information stored? Is it in text documents? Is it in XML? Is it in Oracle? Is it in MySQL? Is it in DBase? Is it in MongoDB? It doesn't matter, because I can consume that without knowing anything about the storage or the server that is serving that up. How old is the software on the server? It doesn't matter. And if there's something in the information I want to learn more about, I can just find it by following the hyperlink. It's simple, it's scalable, and it's effortless. In other words, it just works. And we've gotten so used to having limitless information available at our fingertips that it's actually worth taking a step back to appreciate how truly awe-inspiring this achievement really is. But here's the thing. This vague but exciting proposal took a few years to get any real attention. And this was back when a directory of everybody on the internet was about the size of a phone book. This is an actual directory of the internet from the early 80s. And I have the name and address and email address of every single person on the internet. Can you imagine what that book would look like today? Actually, never mind. No, I can't imagine what it would look like. It would look like the internet. But if you're wondering why what I'm about to tell you is so important, if it's so important that you've never heard of it, just realize it takes time for an idea to reach its tipping point. So when Tim Berners-Lee presented this proposal, the reaction was, so what? Like, there's nothing new here. There's nothing groundbreaking. When he proposed this, like, hypertext had been around for decades. And a lot of these ideas have been around for decades. It took a little bit of time for the penny to really drop. And once it did, it exploded. And here we are today. We are coming from all over the world, connecting over this medium to talk about what's happening next. It took some time for the penny to drop, but when it did, it blew up. And the penny is about to drop on linked data. And here's why. There's a problem shift happening in technology. Now, I used to feel imposter syndrome over my extensive Stack Overflow driven development, SODD. But now I realize the truth. I realize that what's happened is we've just shifted. We've shifted to working on harder and harder problems. And we spend less time on the little mundane details. Got an error message? Bing it. I want to build a complex distributed system and I have no idea how to manage it. Oh, I can just drop in Kubernetes and write a couple YAML files and now my 1,000 microservices can manage themselves. You want a dynamic web UI? Well, I don't have to worry about the nitty-gritties of DOM manipulation, Angular, Vue, React, take your pick. So much complexity has been abstracted away that we can focus on harder and harder problems. And overwhelmingly, those harder and harder problems are falling into a single category. They're surrounding data and data integration. In fact, there's an interesting case study here. Back in 2016, the city of Austin, Texas, and Uber and Lyft were at a little bit of a standoff. You see, the city wanted these rideshare companies to put their drivers through the same kind of background checks and verification that a taxi driver would have to go through. Now, Lyft and Uber, they had their own process, which they thought was sufficient. The city of Austin disagreed, and they were at a standoff for some time. And then finally, Austin pushed the issue and said, either comply with our laws or get out of town. Lyft and Uber both called their bluff, and they said, all right, we'll get out of town. And they did. Within 72 hours, new rideshare apps were launched, were live, were running. That's what it took. A little over a decade ago, it took Uber a couple of years to build their platform. Today, it takes days. Why? The knowledge is out there. We have access to it. The hard problem is just integration, getting all of these different data sources and integrating them into the app. And because we have the web, we have a platform to share and expose this data. And we can consume it, pump it right into our apps, and we can start doing things that were difficult a couple of years ago effortlessly. And not only that, data drives insights. So many of the new and emerging problems are around data. And a good example of this that we've seen accelerating was Tycho Brahe, who spent his life documenting the positions of the stars and planets. Now, although the book here, Rudolphine Tales, is a little bit of a dry read, it also happens to be written in Latin. It was instrumental in launching the scientific revolution. On the heels of just having some good data to start with, folks like Kepler and Galileo were able to analyze this data over a period of years and started to identify the patterns and ultimately began drawing important conclusions about how the entire universe works. Now, we don't have to do that anymore. We have machines and algorithms that are faster and better at identifying these patterns than humans are. And we get unimaginable value from data. And in fact, there's an entire data economy now. It's getting to the point where what we do as an industry is we just gather as much data as we can, and we're going to figure out what we can do with it later. And as a result, we've begun to generate and collect a lot of data. And I do mean a lot. 3 years ago, IBM observed that 90% of the data that we have was generated just in the last 24 months at 2.5 exabytes of data a day. And it's safe to say that was 3 years ago. The data is growing much faster now. And it's driven by a couple of trends. We have more devices. They're ubiquitously connected. And more people are coming online, and we're collecting all of this data, trying to improve efficiencies and everything else. Take all of that, coupled with the fact that storage, the cost of storage keeps plummeting. In fact, it's 15.5 million times cheaper to store data. That's how much it's gone down just in my lifetime. And computing, the cost of computing, the cost per unit of compute keeps going down. And it's interesting that it was in the early 2000s. It was Berkeley, I think. In the early 2000s, Berkeley estimated that about the sum total of all human knowledge throughout all of history was about 12 exabytes. And by 2017, IBM is saying we're generating that 2.5 exabytes consistently, regularly. And in fact, the IDC predicts that by 2025, the total amount of digital data created worldwide will rise to 163 zettabytes. Now, we have exceeded my knowledge of the SI prefixes. I had to look this up. 163 zettabytes is 163 sextillion bytes of data. Right? These lines are not going to converge. 163 sextillion bytes a day. 163 sextillion looks like this. And that's an awful lot of zeros. That's beyond our capacity for comprehension for the most part. So let me put it in real tangible terms. If we had this much data and we stored it on floppy disks, we would need 110 quadrillion floppy disks to store that data. And to give you an idea how many that is, if we started laying those floppy disks out end to end, they would stretch over a light year. That's 5.8 trillion miles. So there's a lot of data, and there's a lot that we can do with it. Here's the nice. That is uncompressed, Jai. Jai asked in the chat, is that compressed or uncompressed? I mean, we can compress it, but a light year is a pretty impressive stat, and I'm going for impact. But yes, although I worry about just how reliable floppy disks are. They're quite prone to corruption. So maybe we want to, if we have the compression, then we need some kind of like CRC or something in there, parity check. So maybe that offsets the difference a little bit. But uncompressed, to Jai's point, 5.8 trillion miles or over a light year. So there's a lot of data and lots that we can do with it. The problem is, where is the data? All over the place. We're back to the Wild West. You want to consume some data? That means you need to connect into a custom app on a server hosting its own custom information system with its own commands and quirks and its own method of organizing information. You need to look somewhere else? Start all over again by reading the API docs. Let's look at a concrete example for a moment. If I wanted to integrate this data programmatically, I would probably request a JSON document. Now, how would you integrate this? Well, first you'd need to parse the structure, and then you'd need to figure out if you're creating a record or updating a record. Like, in other words, which Michael? Then we need to sanitize this data. Well, is that July 10th or October 7th? Because it could be either. And you'd need to read the API docs to figure it out. A person would need to read the API docs. Then you need to disambiguate Wyoming. Do you mean the state or, one of these? And this is the problem. When we write software, when we build systems, we're not thinking about the broader world. We're thinking about functional requirements and deadlines, and does it make sense to me? I built the system, so all of this is obvious. I know which Wyoming. I know who Michael is. I know what I mean by 710, but you don't. Then I need to store all this data. Do we even have all of these columns in our MySQL or a SQL Server or Oracle or whatever? And so ultimately this means that this is the exact same problem that Sir Tim Berners-Lee was facing 30 some odd years ago. Want to query some data? Well, you better start writing some custom code. You want to integrate the data? Well, you better start writing some custom code. You want to store that data? Well, get the analysts involved, get a DBA involved, get a developer involved, spend a week or more, and then repeat infinitely. This will not scale. You will never catch up. These lines will not converge. Okay. Well, what are the alternatives? Well, years ago, when I was a DBA, don't hold that against me. I kid, but my favorite, there are a number of jokes. My favorite DBA joke is, you know what DBA stands for, right? Don't bother asking. And there are many. My favorite from Ken Cousin, a speaker on the No Fluff Just Stuff tour, was a query walks into a bar or a restaurant, selects 2 tables, and says, "Do you mind if I join you?" Yeah, that's really bad. I'll show myself out. But back in those days, we tried to solve this. We had all this data scattered all over the place. Well, we're going to centralize it. We're going to come up with one schema to rule them all. We're going to put everything into an enterprise data warehouse. Of course, the reality was never as pretty as we hoped it would be. You don't see a lot of these today for a number of reasons. It just ultimately didn't work. But now we're watching a new movie with the same name, the same centralized consensus-driven approach in the form of an enterprise knowledge graph. And the problem is the centralized consensus-driven approaches, they haven't worked in the past. And even though we have some advantages, because one of the biggest strikes against an enterprise data warehouse was the schemas were so rigid. You want to add a column on a table with 11 billion rows? Good luck with that. Now, EKGs are graph-based, which give them a little more flexibility, but you suffer from some of the same problems. You still need wide consensus. And if there's anything I learned this week, that getting any kind of wide consensus is an uphill struggle. I'll leave it at that. Not only that, by 2017, we were generating 2.5 exabytes of data a day. Exponentially more now. This isn't going to slow down. So much data out there, and a lot of it is actually actionable and usable. So I'll say it again, you will never catch up. Now, this is a bleak message to be kind of getting to 2/3 of the way through the webinar. So let's come back to this. What are the alternatives? Because beyond how asymmetric data production and data consumption currently is, imagine what the web would look like if they took a centralized consensus-driven approach. And there was a company somewhere that was the web, and they had teams that would manually convert all the information that was out there into their own format as it was created, what we would have is an infinitesimal fraction of what we do have, what we currently have today. And there's a reason that services like this, and this, and this, and this are all footnotes in history. Like, these approaches were a nice idea, but in the absence of better ideas, but it's not the 1980s anymore. Consensus-driven, centralized approaches to information management have tried to kick against the gods over and over again, and they consistently fail. It is inevitable. The web succeeded precisely because it wasn't centralized. We didn't have to put resources into the web. We left everything where it is, and instead we put the web into our resources. Now, we can do the same with data. Now, there are non-trivial problems that need to be solved. And there are at least three heterogeneity problems that need to be solved. And the heterogeneity problems are syntactic heterogeneity. In other words, is the data that we want to integrate even in the same formats? And then there's structural heterogeneity. Are the data shapes compatible? Can I put this jagged hierarchy in XML into my flat SQL table? How am I going to make that work? And the last is semantic heterogeneity. In other words, do we unambiguously know what the data attributes in each silo is talking about? Now, we've been solving these bit by bit. We have common serialization formats that solve number one. And moving towards more flexible, schemaless, or graph-based data stores start to solve number two. And in fact, that's one of the advantages of a knowledge graph in general, because graphs are such flexible data structures. Where we get into problems with a centralized enterprise knowledge graph, a consensus-driven enterprise knowledge graph, is the semantics. Well, if we're going to centralize this, then we need to define and prescribe a global ontology or global vocabulary about what we're talking about, which is extremely limited. And sometimes they're like, okay, well, we'll have a couple ontologies. We'll have a couple vocabularies we're going to use to describe the data. But again, the consensus-driven approaches generally fail. But fortunately, all three of these heterogeneity problems have been solved years ago by existing standards that have been around for over a decade. So let's talk about how we get there. Well, first we need a flexible data model. And because the reality is, if we're going to integrate data sources that are in different shapes, we need to figure out some way to break this up into more flexible units. Now, I'm not saying that it's necessary to take our MongoDB and restructure it as a graph, or take Oracle and move everything into Neo4j. We can leave everything where it is. The standards don't care where your data stores, just like the web doesn't care if you've got Nuxt fronting Vue on a Firebase that is assembling a web page on the fly, or if it's a static text document. It doesn't matter where the data is stored. So one of the ways that we can create any of these data structures, data shapes, data storage methods into something a little more reusable is we can convert them down to name-value pairs. And we can convert them back, and we see this a lot. And in fact, JSON is fundamentally just decontextualized name-value pairs that are sort of grouped together. Okay, so we've done that. We've got a more flexible data model. But now we get to the other. So this basically solves the syntactic heterogeneity, and maybe the structural, because we can kind of move these things around. But we're still kind of struggling on identity and semantics. 6995. What does that mean? Nothing. I mean, maybe it means something to me in the context of my people table in my internal database, but that doesn't map to anything else anywhere at all. So as a global identifier, it has zero value. In other words, we need a universal identifier outside of my little fiefdom. And fortunately, we solved this problem about 30 years ago. And in fact, this system of universal identity works so well that we don't even think about it. We use these to exchange identifiers between machines, between technical people, between technical and non-technical people. It just works. And there can never be a collision because I control my namespace. And this, I don't have to change my primary key in my database. I can just add some context to it to make it not a local identity, but a universal identity. And now you get kind of tricky. What is identity? Because maybe I don't belong to the example.com organization. I belong to me. So this URI, maybe it's a document about me, or maybe it's an identifier that just straight means me. So we can restructure this a little bit and say, oh, well, when I say w3id.org, or when I say my ID, I mean w3id.org/people/r Michael Carey, and we can semantically link these two, saying, oh, by the way, this and this are about the same thing, in a way that machines innately understand. So we've disambiguated local and global identifiers. And we've got an example.com, which is a document about me, but my W3ID is me. That's my identity. There are many like it, but this one is mine. And so the next thing, now that we're clear on who I am and how to connect alternative identifiers that are the same, and we can even discover those and infer those automatically and programmatically without writing a lot of custom code, we still have these name-value pairs that we know are unambiguously about me. So the next challenge, what do I mean when I say birth date or birthday or B-day or DOB or birthday time or whatever we want to call it? Well, we need a standard vocabulary. There needs to be some kind of agreement on what things mean. And you might be thinking, well, wait, didn't you just say consensus is impossible? Yeah, consensus is impossible. Globally, consensus is impossible. But what we can do is I can define my vocabulary, and you can define yours, and then we can agree on where they overlap. And we can use multiple vocabularies, multiple ontologies. So we need, rather than just a random string of characters so that a programmer and an API that's hard-coded to look for certain properties in a JSON document, we need something better that a machine can understand, that a human can understand, that we don't need to read a lot of documentation and write a lot of custom code to begin to work with. So we need that standard vocabulary. And we don't have to create these in most cases. They exist. They've existed for a long time in so many different domains. People, organizations, industries, events, pizza, right? You name it. There are ontologies defined out there. And the more you dive into this, the more you realize these vocabularies are ready and waiting for us to use them. And if they don't exist, we can create them, we can extend them, and then we can map them to other ontologies. So each term in these vocabularies is just another unambiguous name. And you might be starting to see where I'm going with this. And actually, we've got a question in there, birth date format MMDD. However we decide to store this, that just becomes part of that ontology, that whatever the kind of constraints around that go with it. So when we say unambiguously what birth date is, it will also include other kind of important things that a program can discover itself, just like a web crawler on the web can discover more content. And so we link these to an unambiguous name that has standards defined around it. And when I talk about an unambiguous name, this is an unambiguous name, so let's give these unambiguous names. So we put a link in that name. In other words, we just link the data. So here, where we have name, my JSON document calls it name. And I've got birth date and birthplace. But under the hood, in this link, I'm adding some additional context in here. So when I say name, I mean schema.org/people/name. When I say birth date, I mean explicitly schema.org/people/birth-date. And it actually doesn't matter what I label these, as long as I have the link that gives context that communicates that when I say birthplace, I mean schema.org/people/birthplace. birthplace. And so not only does this tell me what the field name means, it tells me how to interpret the value. And this is amazing. This is where we get the intuitive nature of the web. If I've never seen this term before, guess what happens if I click on this link? And so we're starting to expand a little beyond. So there's a question there. How is this different from SOAP? We're going to get to that. There's a lot different. There's a lot of difference in SOAP. Well, SOAP as a protocol. We'll come to that because I don't know if you're asking about SOAP as it relates to XML as a serialization format versus JSON, or the architectural decisions around SOAP that and what a SOAP endpoint represents versus a REST endpoint. But this is kind of ambiguous from all of these things. And yeah, Jeff, we're talking about schemas that work in any format. Yeah. And in fact, this is a REST API, not a particularly useful one, but one that I put together to kind of play around with some of these things. But what we're looking at here is agnostic of protocol. It's agnostic of serialization format. It's just a way of expressing facts with schemas that can be understood. So if we look at this. If we look at statements like this, we're just every name value pair is essentially just a statement of fact. Michael is from Wyoming. Michael's birthday is July 10th. And we've just expanded this from name value pairs where there are 2 parts to 3 parts. Right? We have in these cases a subject that's me, a relationship that is how the data, the value, connects to the subject. In this case, the relationship is birthday, and then the value is July 10th. So we have a subject, a relationship, and a value, or in the terms that we use in this field, a subject, a predicate, and an object. Now, an object can be a literal value, or an object can be another link. And so think about this. Every single statement of fact here, single atomic fact, is essentially identical to a property in a BSON document in MongoDB, or a cell in a SQL table, or a node on a graph. So we call these triples because they have these 3 parts. There are other structures, like there are quads, but triples are very common, and they have those 3 parts. So we add the links into this. Michael, instead of just saying Michael, in here I have embedded the link to my identity, example.org/people/Michael, or example.org/people/ID/6995, or whatever we're using as an identifier. And this is why, by the way, stable names begin to matter. This is one of those things that was absolutely kind of a key point in Dr. Fielding's thesis on REST, and very central to the notion of REST. And it's one of those things that developers look at and they're like, I don't understand why this is a thing. I'm going to make an unstable name so that the name of the resource changes when I change the representation of that resource in a new API. This is one of the reasons why identity is more important than we sometimes give it credence to. But we add these links. So I've got a link that tells me unambiguously who Michael is. I have a link that tells me unambiguously what I mean by from, and a link that unambiguously tells me what I mean by Wyoming. And we get some things out of this. Links give us extra information, they remove ambiguity, and they add standardization. And these characteristics make the data more reusable. So we could serialize this into a single fact. We've got a subject, predicate, and object that we can express different ways. This is a single line in an N triple file, which is one serialization format. We can also serialize a fact using Turtle, which is the terse RDF serialization format. And this is just, and we're doing the same thing. So we can say, okay, well, we're using these ontologies and these prefixes. So I've got Michael, who's a schema person, whose schema birth date is July 10th, and schema birthplace is, and then I'm linking to an article about Wyoming in DBpedia. And we don't have to worry about getting consensus on a global ontology. We can just pull in whatever ontologies that we need. And an application that understands these standards that is consuming this can just go pull whatever context they need because the ontologies are linked. And so we can discover new ontologies, and we can even use ontology alignment techniques to be like, oh, here and here, these two ontologies are talking about the same thing. And then we can turn on semantic reasoning and inference as well. So this, what we've just described, is the foundation of RDF. By the way, just to let you know, we're probably going to go about 5 minutes over, so I want to set that expectation right now. But this is the foundation of RDF, the Resource Description Framework. This is a standard that's been around for about 2 decades. All it is breaking data into its atomic units, its smallest irreducible form. They're self-contained and they're self-explanatory. And each fact is just a fragment in a graph. So if I have one data source that has birthplace and another data source that has birth date, any tool, any library that understands these concepts and follows the standards, the data will just snap together. I don't have to write parsers. I don't have to write a bunch of code to do mapping. It just snaps together like Lego. And so think about this for a moment as an actual real-world use case. Your job is to integrate and merge 3 separate JSON documents. So what would you do with these 3 documents? How much code would you write to merge these? Now, none of the names match up, and none of the formats are the same. There's obviously some overlap, so what would the graph look like? It would look like a mess. In fact, how do you even know these docs are even about the same person? And if you don't control the data sources, you'd have to fall back on rules and heuristics and lots of custom logic and lots of reading the API. Or I can give these 3 JSON documents to any standards-compliant parsing tool or library and get this graph. There it is, 3 different JSON documents, 3 different structures, 3 different sets of ontologies in terms of what we're calling these things, one cohesive graph about me. No redundancy, no ambiguity, no custom code. Now, this might be magic, right? Because how can I go from this to this automatically? Because this is not RDF, right? Right? Are you sure? Because this is nothing new. You might have had this capability for years and didn't even know it. Like I said earlier, JSON is fundamentally just decontextualized name-value pairs, but maybe this isn't just JSON, and these name-value pairs aren't decontextualized. Maybe this was lurking in the header all along, a context to map a JSON name, a JSON property name, to an ontology, to an unambiguous vocabulary. Because in 2010, the W3C began working on an expansion of JSON 10 years ago to include linked data, and the result is something called JSON LD. And JSON LD is designed around the concept of context to provide additional mappings from JSON to an RDF model. So this could have been part of your JSON APIs for years, and you just didn't have eyes to see yet or ears to hear. And maybe this doesn't exist yet for an API that you're consuming, but you can just inject a context and you get all of these capabilities, or you can embed the context. So here, we're using prefixes and we're using unambiguous names. Now, this is great on something new, but if you've got an existing API, you don't want to break all the clients, then put the context somewhere else. Thank you for joining us. Like I said, I know we're going to go just a couple minutes over time, but the recording is available if you want to get to the punchline at the end. But anyway, another question, now that you have these unambiguous names and your data can just automatically, is automatically understandable to a machine, what if the API changes? What if you add a field? What if you change a name? It doesn't matter. Our graphs just get bigger. And I want to go back to the robots for a moment, because if you don't quite see how powerful this is, I want to give you one more example to give it some context. So yes, we now have robots that clean up behind us. We have robots that mow our lawn. Now, arguably, both of these problems a few years ago was like, this is the future, and now we look at this and say, this is not a particularly difficult problem to solve. So what about these robots? Now, for the longest time, I'm going to try to be kind. I'm not going to use the wake word as the colloquial name for the thing, just in case you've got speakers instead of headphones. I'm going to call it an Echo, which is what it is. But for the longest time, my Echo was just a lazy jukebox and a weather vane. That's all it was. I had a lot of money on a jukebox that I could talk to and a weather vane that would that would save me the effort of walking 5 steps to my window and looking outside. But now I ask my Echo very specific questions, and increasingly it knows how to answer them. These are just screenshots from the history. These are not things that I was quizzing my Echo on for the purpose of this talk. This is just something I wanted to do. Now, and it's amazing what's possible. And if you look at this, there are 3 big challenges: speak transition, transcription, natural language processing, and knowing the answers. 1 and 2 are commodities, right? There are libraries we can grab. There are cloud services that are available. Number 3 is the hard part. And increasingly, the data is the hard part. And it's just not feasible at Apple or Amazon for a team of developers to be continuously writing custom integrations and ETL jobs to increase the Echo's knowledge. That doesn't scale. That's not going to work. It's also not necessary. The Echo can find and report all these facts on its own. And in fact, what we know of as Siri was absolutely technology bought for a company that was developing exactly this, using the concepts that we're talking about. Google's done the same thing, and Amazon, I don't have a lot of insight, but I'm sure they're doing the same thing. So they're pulling data from elsewhere. Oh, also Watson, that won at Jeopardy. Linked data and discovering open linked data is how it built its knowledge base. And it wasn't just a lot of people programming facts into Watson. It was Watson being able to consume all of the data that's out there. So in theory, there's a lot of information out there. So in theory, Amazon could have built a massive cluster. I mean, they certainly have the compute resource of machines to do something like take all of Wikipedia and do some kind of natural language processing and document decomposition and turn it into a database of facts at great expense over a period of years. But they didn't need to. It was already done. Volunteers did this well over a decade ago. They looked at Wikipedia and said, hey, this information is great, but we want the data. And we don't want a human in the middle to have to parse it. And so they started taking apart Wikipedia articles and putting them and expressing them as triples, as individual facts. And now we have something called DBpedia, which contains 9.5 billion facts and counting. In other words, they saw the potential and they started building this out. And then in 2007, other folks saw the potential of this and the revolution that it was brewing, and they started publishing their own data as open linked data. Now, open linked data is a choice, just like open information on the web is a choice. You can secure stuff, you can lock it down, you can have validation, all of this. It's just like the web. So don't think that you have to publish everything to do this as linked data. So people started pursuing this. They said, we're going to publish our data as open linked data as well. And these data sets began to connect to each other, and thus began the linked open data project. And within a couple months, they more than doubled the number of data sets in this space, and it grew and grew and grew. And in fact, it takes about a second for this slide to load because this is an SVG with all of the data embedded to it. In fact, if you go to LOD.net, you'll get the entire graph, and if you click on it, it gives you the interactive SVG, and you can see the relationships and everything. These data sources are getting integrated almost as fast as they come online, and this is just public data. So if we look at some of the recent Echo questions, don't judge me, I asked the question, who is the lead singer of Hootie and the Blowfish? And my Echo very quickly responded that would be Darius Rucker, apparently. And so obviously they could have satisfied just this question with public linked data way back in 2007, because they could use DBpedia and one of the already integrated music data sets. But Amazon isn't just doing that. They're not just integrating external data sets. They're taking all of their data and putting it into these formats. And so by embracing these standards, they're able to operationalize everything institutionally that they know. They've got reviews, they've got questions and answers, pictures, ratings, sales figures. They're linking all of these data sets. So Amazon is wholeheartedly embracing these ideas, and they're rapidly building innovative new products as a result. The question is, who else? Well, it turns out it's a lot of folks. And as cool as this is, it doesn't mean we want to blindly integrate everything. We want to be careful. Sometimes people just will publish linked data and somebody will consume it blindly. And I was looking for this. This is an actual image that floats around. And I actually, so I looked for the image, and this is the image that floats around. I assume Google's probably fixed this by now. I use Bing. They take some time to catch up. And it's funny, I just typed this in to find the image, and Bing immediately said, oh yeah, Thomas Running invented running when he tried to walk twice at the same time. So you want to trust the data, but baked right in. I mean, these standards have been around for decades. So provenance chains are there. Digital signatures are there. You can put whatever quality gates are there. You can introduce constraints and semantic analysis using tools like Shackle. And you can query things that match patterns, and you can deal with what you want to trust and what you don't want to trust. Although, interestingly, if you ask an Echo, you get the right answer. And we're seeing this pop up everywhere now. Linked data is being embedded in emails, and companies like Google are giving you really useful views as a result. 48% of the web now contains elements of linked data. 48% of the entire indexable web. And not only that, search engines are pulling that back out and giving you meaningful results as meaningful responses as a result. Not just, oh, here are documents that are about the thing you're searching for. Here's very real stuff. Here are concert dates. Here's its own thing. So they're using published linked data to enrich search results. And increasingly, systems are just dynamically integrating these things. And so you're wondering, well, if folks aren't just sucking all this data into a giant Neo4j cluster, and they're not employing tens of thousands of people to write and maintain API clients and ETL jobs, how can this possibly work? Well, we've solved part of the problem, but how about querying the data and interacting with the data? And we need a simple way to ask a server that we've never spoken to before if it knows anything about anything. And this is the way we do it with the web. I'll just say head example.com/people/Michael, and I get a 3-digit response code. 200, yes, I know what you're talking about. 404, I don't know what you're talking about. 403, you're not allowed to ask this. 401, who are you? But we can do the same thing to talk to open data. I can just say, hey, do you have anything named Wyoming? And it'll say, yes. Oh, I might be interested in you as a data source. This is a trivial example, but this is one of the simplest asks that you can ask of a data source through a standard API. And then I can keep digging. So, okay, give me any resources that have an object of Wyoming, or any resources that specifically have a name in English language of Wyoming. And then I can ask to describe what it knows about these things, and I can do that even if the data source uses an entirely different vocabulary to mine. So this is something called Sparkle. And so far, we've talked about some of the concepts, JSON-LD, and JSON-LD solves part of the problem, and integration is great, but if you don't know what you know and how to find what you don't and learn new things from existing data, there's going to be a ceiling on this potential. When I was a DBA, I liked to dive right into the data. You had an API, that's great, but I want to do things your API won't let me do. I want to find relationships and all of this stuff. So Sparkle is an RDF query language. In fact, that's what the RQL stands for, and the SP is Sparkle Protocol AND. It's a semantic query language for data sets, and you can retrieve and manipulate data. You can do semantic reasoning and inference to create new graphs, discover relationships on the fly. This was made a standard in 2008, and the standard was updated in 2013. So again, this is nothing new. But the pieces are starting to come together. The whole thing is graph-oriented. Your where clause is graph patterns, and your select output is graph patterns. The kind of queries that you can operate are select, right? I can just say select anything that matches a given graph pattern. It can be simple. It can be enormously complex. If I have multiple discrete data sources kind of scattered around, I can push and scatter gather in the Sparkle protocol. And I can, and my graph pattern can even do semantic inference and reasoning, and find matches that don't have explicit matches, even if I'm bringing in data sources that I've never talked to before. I can do an ask and say, hey, do you have anything that matches this pattern? If the answer is yes, I might be interested in you as a data source. And remember, because I don't have to write custom software, this doesn't have to be a big, complicated effort. I could do this all day long. Do you know anything about X? Do you know anything about X? Again and again and again. If so, tell me what you know. So in addition to matching graph patterns, we can create entirely new graphs based on what we already know, and describe tells us what we know, and we get a graph back about what's there. And the cool thing about the protocol is it allows me to push queries to the server. We can do things with a Sparkle API that we simply cannot do with REST. And as cool as GraphQL is, GraphQL gives you about that much of what Sparkle gives you. The whole thing is insanely powerful, and it represents a single uniform API standard that allows us to query graphs and subgraphs and discover new data sources, integrate them, and even infer these new relationships from the existing data in a unified standard way. I really need to wrap this up, so just a couple more really quick points. If you want to start moving in this direction, what does it take? How do we get there? Well, we don't need to change the tools that we use. We don't need to reinvent the wheel. Take a single REST API that you have and wrap it in a way that is forward-looking. And by forward-looking, I mean basically only level 2 maturity on the REST maturity scale. So forward-looking in this case means stable identifiers. In other words, you don't change the URI just because you change the version of your API. Content negotiation, support content negotiation. So next we have to be able to link these resources to other resources. The connections can be captured, they can be generated on the fly, they can be generated on the server, they can be generated on the client. We don't have to co-locate data. We can leave all the data where it is in whatever it is. And we can build our link sets, or we can discover links at the edge. And in fact, if you've got an Oracle data or a SQL Server data or MySQL or Postgres or any relational database, you can get something like D2RQ and layer that on top of your existing relational database and get a Sparkle endpoint in minutes. The key is you want to do this incrementally, stay with whatever your preferred technologies are, and follow the principles. Use URIs as names for things. Use HTTP URIs so people can actually look those up. And when somebody looks up a URI, give them something useful, whether it's a document or, and depending on what they're asking for, give them the docs if they're asking for HTML, or give them the ontology if they're asking for RDF XML or RDF star or JSON LD or turtle or N triples or whatever. And include links to other URIs to facilitate finding more data. And I want to leave you with this as just one example of how powerful this is and how this is going to push us to a web scale revolution, but with data. Many years ago, some researchers realized there was a problem. That yes, we have all this information, but all of these journal articles, and PubMed is a journal for biomedical literature, studies get published, and there are key insights in there, and there are discoveries, and they're locked in journal articles and research papers that are written for humans to consume and not for machines. In other words, it's like reading 1,000 volumes of somebody's journal instead of a single copy of Rudolphine Tales that has just the data that we can start to work with. And researchers realize that despite the explosion of information, there's a ceiling. Instead of ushering in a new era of biomedical insight, the growing abundance of data on the web has intensified the need to develop new approaches to manage and integrate it. If we fail to do so, knowledge will remain fractured, encoded in a myriad of representational dialects, and effectively inaccessible to the majority of researchers. So they wanted to do something meaningful with this information. Step 1 was document decomposition. That's fairly easy today. Step 2 is enriching the data that they had by linking in additional data sets. And again, this was easy for them because RDF solved so many integration issues. And the result was a startlingly powerful way to leverage the data that they already had. They took the data they already had in the sources that it was already in, and they overlaid an RDF representation, exposed a Sparkle endpoint, and suddenly they could discover in hours what used to take weeks, months, or even years. And the first question they asked was this. Imagine you are a researcher trying to come up with new treatments for Alzheimer's, which is a horrible disease. Are there genetic markers? Are there things that we can look for? Are there drugs that we might not be thinking of that might work? Well, you can't ask 10 million journal articles that question. And so they started with a single observation. Alzheimer's patients typically exhibit particularly damaged pyramidal neurons. Now, what are the pyramidal neurons for? Well, they're instrumental in signal transduction processes. Signal transduction processes are actually very druggable. In other words, you can compensate for this with drugs. So they wanted to find a couple of things. What are all the signal transduction processes in the nervous system that are connected to pyramidal neurons, and what are the genes that control these? If you asked a semantic index of PubMed, you would get thousands or hundred thousands of hits and 0 results. They asked their data, their single unified API, this exact question. They got 40 hits, 40 results. It didn't require a special API. It didn't require a custom data set. It didn't require an ETL job, custom code, just a query to a standards-compliant endpoint fronting standards-compliant data. And the result was immediate, real, actionable data. By leveraging linked data principles and standards, they transformed journal articles into standardized data, individual facts ready to answer questions as quickly as you can think of them. This is the kind of power that we want to see in the world. If we go back to the Stack Overflow example, if we just connect the data, the actual data, then we don't even need to look up Stack Overflow. Like, it is mind-boggling what is possible with these standards and these ideas that have been around for 2 decades. And this paper was published 12 years ago. People keep saying, when is the semantic web going to happen? It is here, and it's going to change everything. Thank you, folks.